All right, guys, sorry for the wait. Just setting up the Zoom meeting. All right, I'm gonna get started then. So, before we get into the lectures, more announcements. We're gonna have a first general body meeting at 4:30 to 6 p.m. Sunday, same room as this one. This will become a weekly thing. So this will be for if you're working on a project, if you're interested in doing an IP, if you're doing competitions, if you're on an internal development team. If there's any website people here, please come to that as well. You can also use this time to ask more questions about lectures. But yeah, again, this is going to be our more hands-on, less structured time. But yeah, again, ask me any questions if you know you want to know about the general body meeting. But yeah, again, if you're working on a project though, general body meetings will be mandatory. We're gonna start IPs officially. I'll just skip to the last bullet point. We'll be starting IPs or interest projects officially starting from next week. So please get those forms in, get those ideas in. Again, it's totally fine if you don't have an idea. We can just pair you up with someone else or put you in another group. But yeah. And then the final thing is our first big event for this year is Introduction to Undergrad Research, or Intro UGrad. We're doing that in conjunction with Link Lab. And so this will be more of a panel style where myself and some, actually maybe not me, but some other undergraduates, upperclassmen who have done machine learning research, as well as one faculty member and a couple of PhD students. We'll be talking about our perspectives on research, how we all got into research, some of the strategies, some of the emails we've sent, things like that. I highly recommend it if you are considering, doing a research with a professor. And as always, we do all of this stuff is on Discord as well as more information. Please let me know, please join ASAP if you haven't already. All right, just another few seconds just to set up the recording again.
Have you started the meeting yet?
Yeah, I have. I guess it's. Okay. All right. So back to the real lecture. Any questions about events or forums or anything like that? All right, perfect. Okay, one more thing. As always, this current lecture and soonest recording will be on the website. So if you want to follow along like through the slides on your own side, like feel free to scan the QR code and get started. But again, uh, you know, all the recordings and lectures are on the website. Okay, so review. Last time we covered a neuron or a perceptron when it was used by itself, as well as like what is a neural network in general. So a quick recap. A neuron is a building block of a neural network, but you could also use it as a single deep learning model. So in this case, so for at inputs, you would call each input, like each column in the input a feature. So in this case, right, if you remember, we were working with weather prediction, right? So we have the weather data for a single day. And, some of the things we cared about were humidity, temperature, and wind speed. And so we use each of these factors, these features, to make our final prediction, which was rainfall in millimeters. Does anyone remember what type of problem setup this is? Is it unsupervised or supervised? All right, I heard someone whisper supervised. Is it classification or regression? Since we're predicting a continuous number. Regression, perfect. Yeah. Okay. And so within this neuron, right, we have weights for each feature, one weight per feature. And we multiply the weights by the feature value to get a weighted sum, right? And so again, weights are just really any number, any continuous number that gets us a weighted sum that looks good. So like these are just one possible set of weights. They could really be anything as long as they get us to this 36.5, right?
This is like AI, I guess, makes the weights or just the program with the weights.
Perfect question. Last time I gave you the weights and the biases, right? But obviously you can't do that. If you remember the Desmos example, it was such a pain just trying to get that thing to work, right? And now imagine you have 30 neurons. It's not feasible, right? So this lecture will cover how does the AI learn to select weights and biases? And remember, the activation function is something we just pick. It's like an extra parameter, right? And in the case of a single neuron, like in isolation, the activation function isn't really that useful, right? Because if you guys remember, a neuron can only do like y equals mx plus b. It can only do linear relationships, right? In other words, it's kind of trash by itself, right? It's algebra 1. The key though is when we kind of put them together in a network, a neural network, right? So by having these neurons together with these non-linear activation functions, again, non-linear is just anything that does not look like a line or a plane, right? So in this case, this activation function, ReLU, it bottoms out everything that's a negative number to 0. So by connecting these neurons together and each of these neurons having a non-linear activation function, we can learn non-linear functions, right? We can model non-linear patterns in our data. So in other words, like if you remember like the housing price example, right? Or really any example in your day-to-day life, anything that's a lot more complicated than like just a line, well, a neural network in theory could model it, in theory, right? Okay, so I already went over that. Okay, so yeah, as O mentioned, before I gave you guys the weights and the biases, but that's not scalable. So how do we pick them? So the process of picking our weights and biases is called training. So there's kind of two main processes in training. There's forward propagation and back propagation. So we actually did forward propagation last lecture. Forward propagation is like for every single input in your data set, you just chuck that through your model, right? You just you just have the model make a prediction. Oh, sorry. You just have your model make a prediction. And remember, that's what we did last time by like multiplying by the weights, adding the bias, throwing to the activation function. What we didn't do last time is assessing how bad, like a metric for how bad our model did. And we call this metric a loss function. Okay, so forward propagation tells us how bad we did, like how off is our model's predictions. Back propagation uses this loss function, like our error, and it uses that error to fix our model. Okay, so let's kind of run through this example that we went through last time. But in practice, you randomly initialize your weights and biases. So in this case, I've randomly initialized the weights and biases. You can see that when you run this input through the neural network, our prediction, y-pred, is minus 0.44. Now let's see, just for the sake of this example, right? This rainfall example. The actual truth, like for this day, the rainfall for this day is 0.5 millimeters. So as you can see, we predicted negative rainfall. Not very good, right? We were very off. So how do we quantify this? Like, how do we quantify how bad we did? Okay, before we get there, I'm just going to try to move to a simpler representation. We've been kind of working with this guy up here, like with our circles and interconnected. This thing is the exact same thing. It's just, I feel it's a little bit easier to just show the weights and biases and like the activation function. Is that clear? Like this is the exact same thing. I'm just trying to illustrate it in a different way. But anyways, back to the question. How do we measure how poorly our model did? So we call this metric the loss. And so there's a few rules with loss. Sorry. One is that we generally like a positive loss. You could work with a negative loss, but it's just simpler if we work with a positive one. And we want, like the goal with training, right, is that we want to choose weights and biases that minimize this loss, bring it as close to 0 as possible. So like, for example, like a loss of 12 is like trash. A loss of 0.03 is like pretty good, right? A loss of 0 is like perfect. Like theoretically, like you can't any better than that. We'll learn a little bit later that if you have a loss of exact 0, it's a little bit suspicious. Like it's a little bit too good. But the point is, we just want loss is a metric of error, and we want that error as low as possible. And another thing is that loss is relative to the problem. So in this example I gave over here, maybe for my problem, like 12 is actually kind of good. Like the theoretical best is like 4 or 3, right? Really, like loss in isolation, like isn't the best metric for evaluating your model. In the sense that if I have two separate problems, the loss for problem A for like rainfall versus a loss for problem B for the housing data set, you can't really compare the two because they're just completely, they don't really like match together. So, okay, let's go through some possible loss functions. Here's like a very naive approach. You just subtract the true value, like what the actual ground truth should be, the label, if you guys remember, from the prediction, right? And you guys might obviously see this is negative, right? Undesirable. So a very easy fix is that we just put absolute value bars around that. So this loss function is called the mean absolute error, right? Very straightforward, just the absolute difference between the two terms. And again, it's always positive, but a nice thing is that it penalizes all differences equally, right? It's linear, right? That might be pretty obvious, but let's compare it to this next loss function. This is mean squared error. So the only difference from this is that we square the difference, right? It's okay. So why bother doing that? Why not just take the absolute error? Well, for one, we know this will be positive, right? If we square anything, it will always be positive. But the really interesting property about this is that it amplifies errors above one, right? So what does that mean? So let's say the difference between the it's a little small down here, but the difference between the truth, like the label, and your prediction is 5, right? So if you square that, then your loss snowballs to 25. It gets amplified. Whereas if it's 0.5, it gets minimized to 0.2, or yeah, not 0.25, square root of 0.5. It gets minimized though, right? And so the point is we're like amplifying, right? Like we're amplifying somewhat big differences and we're minimizing smaller ones. And so you could see that, like, in other words, this is a very harsh loss function. And at times this behavior is desirable. And at times just treating all losses equally is desirable. So really it just depends on your problem. Okay. So we went over loss, right? And hopefully from last lecture, you remember how to just chuck an input through the neural network. So in this case, for our rainfall example, we have a mean squared error of 1.44. And that's really it for forward propagation. You just feed your input through your model, you get the prediction, and then you plug in your prediction into the loss function, you get your loss. It's just that. Any questions about forward propagation? All right, fantastic. All right, back propagation when things try to get a lot more interesting. So there's kind of two goals with back propagation. One is that you want to calculate how much each parameter, and parameter is the term for any trainable number. So in this case, weights and biases. Remember, these are things that we don't want to pick. Like we can pick our activation function, right? But we want the model to learn weights and biases. So these are our parameters. So we want to calculate how much each parameter contributes to the loss. And then once we calculate that like magnitude, we then update each parameter accordingly, right? So for the sake of this example, how much does W2 contribute to the loss? And once we answer that, we can adjust it accordingly. Okay, so again, let's try to like abstract this a little. Let's imagine the loss function as, well, sorry, let's imagine loss, the quantity loss, not the loss function, the quantity loss, as some unknown function in terms of like each of the parameters. So for simplicity, let's just imagine loss as a function in terms of W2, right? So in other words, in this case, like here's what our current W2 looks like in the model. And we have a loss that's around here 0.88, right? And well, obviously we want to lower this loss, right? And so graphically, we can see that, hey, just slide this weight downwards, right? Just increase W2. But numerically, like how do we know this, right? Because again, we don't have access to this nice graph usually. We can't visualize this. And imagine if like what the example was not in 2D. So the way we can kind of know which direction to move our parameter is by taking the derivative of it, right? So in blue, I've kind of drawn the derivative or slope of the of W2, the weight. So in this case, hopefully it should be very clear that the derivative is negative, right? And what that means is, well, increasing W2 would decrease the loss, right? And you could also tell that, hey, like this is a very, very steep slope, which means that the derivative is probably very big. And so, okay, if I were to ask you, given this information about the derivative, you could say that, hey, like if I increase W2, well, then the loss would decrease. And again, that's what the definition of the derivative is. let's go through another example, right? We have, let's say W2 is up here now. Again, you could just hopefully graphically see the slope, right? In this case, the derivative is positive. What that means is increasing W2 increases the loss. Um, so, and the derivative is also a little bit smaller. So a large change in W2 would result in smaller change in loss. And again, to minimize loss, we decrease W2. So is anyone seeing a pattern here in terms of the derivative and how we should move W2? Any hands? Opposite. Exactly. It's the opposite. We just do the opposite of the slope. More formally, we just take the negative of the partial derivative W2 with respect to loss. If you've taken Calc 3, or maybe I'm not sure if this is covered in Calc 3, but if you've taken Calc 3, the term partial should be familiar. If not, it's just a derivative. It's just a derivative in terms of a single variable, right? So in this case, again, in our example where loss is only in terms of one function, well, the partial derivative is just the derivative, right? Okay. So again, more examples. So in this case, let's say numerically, right? Let's say we didn't have access to this nice graph. If you were to just calculate that the partial derivative is minus 3.8, well, you would be able to say that, hey, if I make that positive and move in that direction, we're going to minimize loss. And again, same example. Does this intuition make sense? Like why we take the derivative and how it helps? If not, feel free to ask. It's a little bit of an abstract concept. Okay, perfect. Okay, so naively, we could just say that, hey, the derivative, the negative, yeah. Yeah, yeah. So partial derivatives is just for a yeah. So for a function of multiple variables, so imagine L's a function of all these variables, right? The partial derivative is a derivative with respect to one of the variables. So in this case, I've illustrated the partial derivative for you. It's where you can ignore all the other variables and just take the derivative with respect to one. So in this case, like the partial derivative of W2 with loss is just the derivative, like just a derivative. Again, for our purposes, you can just think of it as like the derivative. Does that help? Okay, yeah. Good question. But yeah, as I was saying, so the derivative, the negative of the derivative tells you what direction to move and roughly by how much, right? So why don't we just update W2 each parameter by just subtracting the derivative from it? Does anyone have any guesses as to why this might not work? Exactly, exactly. In this case, the negative derivative is like 4.99. If you look at our axis, like 0.8 here, 0.8 is here, 0.6 is here. Like minus 4.39 is like all the way, like it's not even on the graph, right? I just had to squish it in there just for argument's sake. But yeah, we're just gonna crazy overshoot. And so what is the possible fix, right? Because we know that this is the general right direction, right? And this magnitude is somewhat useful to us. Very simple. We just have a scalar called the learning rate. It's just a very small number that we multiply by our derivative. Just to scale that change down. So again, in the case of a minus 4.99, multiply that by 0.01, and we're good, right? We take a small step. It's really just that simple. But yeah, and so with a small learning rate, right, we can be much, much safer, right? We can take baby steps that are almost guaranteed to not overshoot. But the trade-off is we'll take a lot more time to train, right? We have to do a lot more iterations. Whereas with a larger training rate, we might go faster, but there's a risk of overshooting, right? But even in this case, right, you can see that we overshot, but we are still closer to the minimum, right? So you might ask, okay, how do we pick this learning rate? And oftentimes, like the naive solution works in this case. You just kind of try a lot of them. The learning rate is a very just common parameter that you set, and you just try multiple. There's also something called a scheduler, where you might start with a larger learning rate, and then over time you decrease it for every iteration. So for example, if you're all the way up here, you might start with a large learning rate, and the closer you get, the smaller your steps become. Okay. And this process of taking the derivative with respect to every parameter and then moving that parameter in that direction, right, towards that minimum is called gradient descent. Because the gradient is a term for all partial derivatives. So in this case, the derivative of W2 is just one element of our gradient. In reality, we'd be calculating like the derivative for W2, W1, B1, B2, all of the parameters at once. And so all of those derivatives at once are called the gradient. And descent because, we're going towards the minimum. And you might ask, okay, let's look at this green guy over here. Well, gradient descent would tell it to just go here, and then it would stop, right? Because what is the derivative down here? 0. And then you're stuck. And so the solution to that would be optimizers. So gradient descent is the principle of like training your neural network. But as you can see, we've already hit we've already messed up. So in the future lectures, we'll talk about optimizers and how we can make this process more intelligent. But this is the general intuition of how backpropagation works. Okay. And so in practice, right, how can we calculate every gradient? And the nice thing is when you code this in PyTorch, like we will in next lecture, it's all handled for you. It's very convenient. When you do a forward pass, right, like you're sending data through your neural network, all of your intermediate values are saved. So in this case, like the value of like the input multiplied by the first weight, like this number 1, that's saved, right? The output of your activation, that's saved. All these numbers are saved. And so you also have access to your activation functions, all of these like all these math operations. So all the information you need to do backpropagation is literally right here. It's all in your forward pass. And so calculating all the gradients is in Python a single function, just one function. So it's very convenient. But yeah, just a recap of backpropagation. I think we've went over this somewhat thoroughly. Any questions though? Okay, perfect. Yeah, perfect. Going a lot faster than I thought it was. Okay. So again, just to recap, the process of training is when you learn the weights and biases needed to make correct predictions. And so kind of rough pseudocode is that you would start by randomly initializing your weights and biases, right? And then for every data point, you do a forward pass, you get your loss, and then you use that loss to do your backwards pass. And so this a synonym for training is another term called fitting. They're not exactly the same, but for our purposes, they're roughly the same. But with training, there are two very, very common types of problems. The first is underfitting. And so this is when your model is too simple and fails to learn the patterns in your data. And there's more causes than this, but these are like the big 3. One is your model is not complex enough. So you just might not have enough neurons to like model the complexity of your function, right? Like let's say I'm trying to learn a classifier between cat and dog. If I have like a single perceptron that can only learn linear relationships, well, that would be guaranteed to underfit. Another thing is that you just didn't train long enough, right? If you remember that graph, the graph of like W2 and loss, like maybe I end training and like I end up in this orange spot. Like I never train long enough to end up down here. So in that case, you would also underfit. And then finally, it's just you might have picked the wrong features in your data set. Feature optimization, feature selection is a very, I guess, prominent research subject, but just generally, you may have just not picked the right features. In our rain scenario, maybe humidity is not useful. And maybe, I don't know, time is a lot more useful metric for rainfall. So there are a lot of different reasons why you can underfit. So you might remember this example from last lecture, but in this case, this is a model with just 2 neurons, right? And so no matter how much I tweak the weights and biases, I will never be able to learn this like kind of sine cosine-esque wave function. And so in this case, the cause of underfitting would be that the model is not complex enough. But yeah. Okay, so the opposite of that is overfitting. And this is when the model not only learns the underlying patterns in your data, but it like essentially memorizes it and learns the noise in the outliers. And so potential reason for this is model complexity. So instead of the model being too short like it is, or too small like it is for underfitting, it might be too large. Like it's so big, it has the capability of grasping all of these little like insignificant patterns that you don't want to learn. You might have trained for too long as well. And then finally, like you just might have a bad data set, right? Maybe your data set like is mostly noise. So there's a plethora of reasons why you could overfit as well. So here's an example. If you were here last lecture, you might remember the idea of a decision boundary, where in a classification problem, you could like almost graph a very simple neural network and like draw a boundary, right? If not, that's totally fine. Just imagine a neural network as like a boundary, right? So what we want is something like this, right? It's learned the general pattern of the data. It's made some mistakes, right? But generally, this is how triangles and circles are separated. Whereas overfitting would learn the exact separation between all of them, right? And so at first glance, this is fine, right? Like, hey, a model did really well. But then when we add more data and the data follows this pattern, like the true pattern of the data, well, now you'll notice that, hey, like it's misclassifying the triangles, right? So the idea with overfitting is that like you memorize the exact patterns in your training data set, right? Remember, your training data set is like a small subset. Like if I want a model that predicts rainfall, like, and I only train it on a years of rainfall, right? If overfitting were to happen, it could perfectly predict it for that year. But then for the next year, it would be completely trash. So is that distinction like, yeah, question?
So essentially, overfitting is good when you have like just a small training set with nothing else. But then once you add more data to it, it's when you get problems.
Yes, sort of. Yeah, you're right in the sense that overfitting is noticeable when you add new data, right? But remember, what is the goal with machine learning in general? It's not necessarily just to like be really, really good at our training data set. Like in this case, the 1 year of data. Our goal is just to learn rainfall, like learn these general broader patterns. Like I don't really need a model that can predict past data. I need a model that can predict future data. So yeah, does that answer your question? Okay, perfect. And so, okay, how are some common ways you can like see the difference between overfitting and underfitting? Well, you kind of broached the subject. We can split our data into a train set and a test set. So the train set is kind of what we've been talking up until now. This is the data that's used to train your model. Like this is how your model's doing its gradient descent, its forward passes, all of that. Your test set is data in your data set that you remove like from training. Like your model never sees it for training. And we use this to like evaluate the true performance of your model. And so generally, you can tell if your model underfits when it's just bad on both. If it's bad on training data, if it's bad on test data, that means it just did not learn the right pattern. Like it didn't really learn any pattern. Overfitting is when it's really, really good at that training data set. Because remember, it's memorized it, right? But the moment you introduce new data, your test data, it has very bad performance, right? And so again, training data is what you use to train the model for propagation, backpropagation. Test data is once your model is fully trained, then you see how good it really is. Is that clear? Okay, perfect. As I mentioned at the very beginning, loss is not, so by the way, change of topic. Loss is not the best evaluation metric, right? It's not like it doesn't apply to all problems like equally. So what are some more fair metrics? So accuracy is kind of the go-to. It's very straightforward. The number of correct predictions divided by the total number of predictions. Very straightforward. It's like a percentage, right? Like you want 100% accuracy, 95% accuracy is fine. Precision and recall are a little bit more interesting. Precision is the number of true positives divided by true positives plus false positives. In other words, the number of true positives divided by all positives predicted by the model. Recall is somewhat similar. It's true positives divided by true positives plus false negatives. So we can use both of these to create a graph like this. And these are just generally called like area under the curve graphs, where you can see this dotted line. This is the model like just completely random, right? So it's true positive, like it's, well, yeah, it's just random chance. And so the perfects, the theoretical perfects would be this green bar, like this corner. In reality, your model will be something like this, but you want it to hug that green line as much as possible. It's totally like, again, the go-to, and I think what we'll be using for our next coding example will just be accuracy. But if you ever read like a machine learning paper or like want to do more rigorous testing, precision recall and area under the curve are great metrics as well. But again, for our purposes, we'll mostly just be focused on accuracy for like the foreseeable future. Yeah, okay. So that's today's lecture is a lot faster. Future lectures will not be an hour long. They will be the 30-minute to 45-minute mark. One thing though is that what I am doing from now on is I've had like the important stuff, the really important stuff in the first 30, 45 minutes. And then I have like extra stuff, like examples, more practice, things like that. So before I get into that, if you haven't done so already, here's the link to the notebook that Vinate has made. We'll again, we won't be working on this now because we haven't really covered PyTorch or coding yet. But if you're feeling ambitious, if you think you can start, go ahead and go nuts, right? What we're doing for next week is we'll make a Discord post about this, but we're gonna make this notebook into like a mini challenge. So right now, the website team has made a leaderboard on the website. And so next week we'll be releasing a data set for this problem. And so, as you train your model, you can also upload it to the grader. And then you can see you can live see like how well your model is doing up against everyone else's. So next Wednesday, I'll be here until like, I don't know, like 10 p.m. or 11 p.m. as late as you guys want to go. And then you guys can just go nuts trying to, get to the top of the scoreboard. In the future, we'll be doing like mini challenges with some prizes, some things at stake. For now, this is just light, light and fun. But yeah, again, we'll be covering coding next lecture though. So don't feel too pressed about that. Again, all this stuff's on the website. But yeah, okay. So now I'm going to go through an actual like example of calculating the gradients for backpropagation, right? Again, as I said, you will never have to do this by hand. The reason I'm going over this is the intuition helps a lot when you're troubleshooting your model. Again, when you're coding a machine learning model, you will never have to do this. It's just the intuition I think is like invaluable. So, okay. This is also where like if you guys like need to leave or anything, like now would be the time. Hey, everyone stayed. Beautiful. Okay. So again, I'm working with this representation of neural network. In this case, I have like a weight and a bias, and then an activation. So these three components are like one neuron. And then I have a output weight and an output bias and no activation. So in other words, I have 4 parameters. In this case, I've randomly chosen the weights and biases for everything. And I have a ReLU activation function. Okay, so just some quick convention out of the way. I'll be denoting pre-activations as Z underscore like some number and activations as A underscore some number. Pre-activation is a number like right before the activation. So input times weight plus bias. So this blue guy. An activation is just that number shot through through ReLU. Okay, so in this case, we'll try to be aware of the formulas. Again, it's just input times weight plus bias, y equals mx plus b. We wrap that around ReLU. And then we multiply that activation by the weight 2 in the bias. Again, hopefully this should be very clear. Everyone following along? Okay. Okay, so now we calculate the loss. You might notice that this isn't technically mean squared error. I have a 1/2 term over here. That's just to make the future calculations easier. In practice, just use mean squared error, right? You'll see how this simplifies things later. But again, this is just chucking this prediction through the loss function, right? So prediction is 1.8, output is 3, loss is 0.72. Standard for propagation. Okay, so how can we use this to now optimize W2? Like actually update W2. So let's kind of retrace our steps. Like how do we get from W2 to the loss, right? Because again, we're not trying to update W1 or B1 right now, just W2 right now. Well, okay, so W2 as input takes A1, and then you add that by the bias, and then you get the Y prediction, right? But we don't stop there. Again, we want to see the relationship between W2 and the loss. So we then take the Y prediction minus Y true, and then square that. And so if you remember from calculus, if I want to take the derivative of loss with respect to W2, we have to use the chain rule. So what that implies is I have to like this derivative is equal to the loss, the derivative of the loss with respect to Y prediction times Y prediction with respect to W2. Again, this is just standard chain rule. Does anyone have any questions about this? Okay, great. So let's actually just go ahead with those calculations. Again, that's why I was like documenting our steps in the forward pass, right? Because now we have all these numbers up here for us, very nice and easy. So, okay, what is the derivative of loss with respect to Y pred? So just consider Y pred as like X. So X minus some constant squared. Well, that would just be Y pred minus Y true, right? Again, that's where that 1/2 term, oh, I dropped it here. That's where that 1/2 term is very useful. In reality, it'd be 1/2 times Y pred minus Y true for MSE. But because I had that 2 up there, like it canceled out. Okay, and then what is the derivative of Y pred with respect to W2? Well, I mean, in this case, like we're on this side of the ReLU, and what's the derivative of a line? 1. Or sorry, not 1. The slope, right? In this case, A1, the input. So yeah, we just multiply those guys together, and now we get this nice partial, which is minus 2.4. Okay, and now we can okay, so we now have this gradient. We are now ready to update W2. So we take minus 2.4, take the negative of it, multiply by the learning rate. In this case, I've chosen a learning rate of minus minus 0.01, sorry, 0.01. And now we can just update our weight. So originally it was 0.8. After the update, it's increased to 0.824. And so you can imagine for the next like iteration of training, like the next time we do back propagation, we might continue to like increase it and like push it in that direction until we hit that minimum of the loss. Okay, so how do we update, like in this case, W1 now? Much, much farther back. Well, in that case, oh, sorry. We have to consider, okay, how do we go from W1 all the way to the loss? So there are more equations, but again, each intermediate equation is just another chain rule, right? So the derivative of loss with respect to W1 is just each of those intermediate equations. So derivative of loss with respect to Y prediction with respect to A1, A1 with respect to Z1, and then finally Z1 with respect to W1. It's just like this chain of calculations, and that's how we calculate that derivative. And I won't go through all of that. Hopefully, hopefully it should be somewhat clear. But yeah, once you calculate that, we've gone from a value of, I think it was 0.5 to minus 1.92. So very big jump. Yeah, hopefully that clears up a little bit how back propagation works. Again, I don't like going this math heavy. This is probably the most math heavy we'll get. Again, if you weren't able to follow along, again, you'll never have to do this by hand, right? So don't feel too discouraged. If you have questions though about the calculations and anything else, feel free to just come up and ask me. Otherwise, that's it for lecture. Again, future lectures will be 35 to 45 minutes long. If you want them longer, let me know. I'm happy to make them longer. But yeah. Thanks for coming, guys.